Greetings, Professor. First, I would like to thank you for giving me this opportunity to present my demo through a video. My name is Sai Kiran Verma and I am from Team 15. And my another teammate is Abu Ali, and currently he isn't available right now. So I would like to talk about my work for the second project, which is like machine learning with the collaboration of R and DBMS. So a few words about machine learning. So machine learning, what would we use it for? Like it can be used for many models, but one we are concentrating right now in this project is about the data patterns. Okay, so we have how do you identify a pattern in the data and what is the necessity of identifying a pattern. So there are few factors in a data which are influenced by the other factors in the same data set, right? So you would like to know the contribution of the each factor with respect to the dependent factor, right? So to calculate that, we have one model called linear regression model. What it does is like it categorizes the data set into a linear equation as of the form y equal to mx plus c. So what it says is that the dependent variable, which in this case is y, is a factor of all the available variable as m into x plus c plus some constant. So I would like to show like how we have implemented linear regression model in this project. This program explains how the linear regression model is calculated through R. So our program is capable of handling the data irrespective of the number of columns in it. So all you need to do is like give us the file name. So we take the file name and create a matrix, and then we try to find the coefficients of the each dependent factors, right? So for example, in a diabetes data set, a patient has to go through multiple series of tests to identify if he is a diabetic or not, right? So we consider the test as x here and the diabetes coefficient as a y. So to calculate y, we fetch the coefficients of the each dependent factors, and then we fetch a pattern out of it. So I would like to run this code and show you the results on the real data set available to us. So it should be run as like so I'll just give the file name. Right now we have a data set called diabetes.csv. So if you see here, these are the calculated coefficient. This says the y-intercept with respect to all the individual available dependent factors. So y is dependent on v1 at 0.02 times and v2 at 0.05 times. So using this, what you could find is like which test is more important in identifying if a person is diabetic or not. So you can even miss like v4 and v5, but this v7, which is contributing like almost 0.14 times. So you know, while in this way you can sort which tests are needed first to calculate to identify if the patient has a diabetes or not. So linear regression helps us in identifying the pattern so that we can quickly find the symptom out of it. So if you see here, using R, we have calculated the linear regression at like 0.12 seconds. But you know, you might wonder, like there are many more technologies available, why we have chosen R in particular. So we would like to show the same linear regression using the database functions by collaborating R with Vertica. Right now we have taken the data set through the local system, but now we would like to take it from the table and apply the linear regression. But before that, to perform this linear regression to the table, you need to construct a matrix called gamma matrix. What is the need of a gamma matrix? Gamma matrix is in simple terms called as a summarization matrix. What it does is like in the machine learning models, there will be many calculations which will be repeated again and again. So the gamma matrix helps you to calculate all the necessary calculations and put it as a matrix, so that as you move forward, you can just refer the object from this matrix and apply it in the code. So we have created, this is the format of the gamma matrix. Okay, so we have created the gamma matrix first. So I would like to show like how we have created the gamma matrix. So if you see this, So what happens is like we take the table name. Previously we used to take the data set, but now we are taking the table name. And once we take the table name, we haven't hard-coded the number of symptoms for each data set, right? Like hard-coding it may not work for the other data set. So what we do is like we first fetch like how many symptoms are there per each person. Okay. Once we fetch it, we create a gamma projection, okay, using the dense gamma function, and we convert that gamma projection into a matrix, okay, into the matrix, and then we find coefficients of the each dependent factors, right? So once we calculate the coefficients, and we can find the pattern. So I would like to run this once. So previously I have given a diabetes data set as a CSV. Now I would like to give it as a table. So diabetes, this diabetes table is available in Vertica, which we are fetching through using Vertica JDBC. So if you see here, the values are same. If you see, there is no difference in the values for the linear regression through R and linear regression through R and Vertica. But if you see, there is a difference of the timing, execution time. So the R takes only 0.12 seconds to calculate the pattern out of a data set, whereas the combination of R with the Vertica, it takes like 0.624. But you can't conclude based on one single set, because if you see this data set, you have only 768 records. We would like to test it more on a bigger, larger data set, right? So I have the data set available, so I would like to show you the linear regression for the bigger data set. So first I would like to run the linear regression based on R only. So the file name I have is like so this might take like considerable amount of time. So I have already noted down the results. So if you see here, so the credit card, this is the diabetes data set information, and this is the credit card information. So the diabetes data set has like only nine symptoms to be known, and like only 768 patients available. Whereas in the credit card, there are like around 8 million. And each record has like around 31 attributes. So this is like a much more larger data set. If you see the time taken for the execution for calculating the linear regression using R for diabetes, it's like only 0.03 seconds, and using Vertica it is 0.6. So you might consider that using R it is much more better. But if you see here for the larger data set, it is taking like around 246.90 seconds. And when the same data set is ran using the Vertica, it takes only 50 seconds. That's a flat 80% lower than the available one, right? So it takes like around 50 seconds. So if you see here, it is still running, because it takes like around 240 seconds to run it. So so as we can say that, you know, as the data set is increasing, we can use we can collaborate the database functions into the R functions to fetch the much more better results. Okay, so next is like naive Bayesian. Why do we use naive Bayesian? So data set can range from like a million to billions of records, right? So you want to find the patterns among it. Like each data set might have a different number of categories available in it. You want to find the standard deviation and the mean of each category available. For example, in the diabetes database, you have two categories available. If the patient is diabetic, he is categorized as a 0, and if he is not diabetic, if the patient is a diabetic, he is categorized as 1, and if he is not diabetic, he is categorized as 0, right? So there could be like many more categories available in other data set, but in diabetes there are only 2. So how would you like to calculate it? Okay, so to calculate it, so this is still running. I would just stop it and I'll just show you how did we calculate it. So if you see here, we are fetching the name of the data set first. It's a table, and then as we have done in previous R plus Vertica, we fetch the symptoms of the each patient, and then what we do is like we segregate the data into the available categories. Okay, so how do you know like what are the number of the categories available? So presently in the most of the data sets, it is categorized as either 1 or 0. So what we do is like we create a table for the category 0 and we create a table for category 1. So using this query, we fetch it and create it. But before doing that, care should be taken that if the table is already existing, this might fail. So our code handles that problem by using drop table if exists. So when it's running for the first time, it doesn't give any problem. But if it runs for the second time without this, it might create a problem. So we have handled that using this drop table if exists. And then once we create a table, what we do is like we find out like how many records, how many patients are diabetic and how many are non-diabetic. And then we create a dense gamma projection like we did previously for the, we can use this projection for creating a gamma matrix, right? So we do two dense gamma functions on like two categories, and we create a gamma matrix out of it. Once we create a gamma matrix out of it, we find the L and Q factors. Okay, if you remember, we use the same factors in this, like in this gamma matrix we have L and Q. We fetch this and we calculate the pattern out of it. So using this, we find the standard deviation R0 and also the also the mean of the data set. So I would like to execute this and show you. So now when I execute this, it will ask for the data set. I'll give for diabetes. So our output shows like, so there are like 500 diabetic patients and 268 non-diabetic patients, and this is the standard deviation for each of the non-diabetic patient for each symptom. Okay, and this is like the standard deviation with respect to the diabetic patient, and this is the mean distribution among them. For category 0, this is the mean distribution and this is the standard distribution. So it takes like around 0.5 seconds to run it through Vertica and R, right? So the same one when ran through only R, it takes around like 0.35 seconds, but using Vertica and gamma matrix, it takes 5 seconds. But when it is run for the larger set like we ran for the last time, it takes around like 263 seconds in using R, whereas using gamma matrix, we can calculate the standard deviation in flat 69 seconds, which is like much more efficient when compared to the normal R, right? So while calculating this, the challenge, I would like to emphasize on the challenges that we have faced. The first challenge we have faced is like data inconsistency, especially while loading the data during the naive Bayes phase. So we faced like few inconsistency in the data, which made the code stop abnormally. So we had to fix it. And one more problem we faced while doing this is like there was a sudden expiration of the license for Vertica, so it has holded our project a bit. And then one major thing which was missing for us is like lack of test data. Right now we have only 2 test data available. So if we had like more test data, like around 3 to 4, it would have been much more helpful in comparing it. So what is the conclude? So what can we conclude from this? We can say that, okay, for the smaller set, as the results show, for the smaller set, R tends to be much more faster when compared to the R+DBMS. But world is not moving with the smaller data set, right? It is evolving. Data is increasing. So we can create the linear regression model, but by using some database functions, by collaborating the database into R, it is much more efficient for the larger data set. I think the research is still going on in this, but the results show that if we collaborate the database into the R, it is much more efficient. Thank you.